Hello, everybody. Welcome back to our Fiveable Stats streams as we prepare for the AP exam coming up in the next few weeks. We have right at a month until the AP exam for AP Stats. So we are in crunch time. I appreciate you all joining us today as we prepare for the stats exam by looking at conditional probability and independence. So we're going to really focus in on those two topics and take a little bit of a different approach to some of those things that maybe you have done in the past. So maybe it'll help some of you. Maybe some of you will stick to the way that you've been doing it before. Be sure to follow Fiveable on, we added TikTok this week. So TikTok, Twitter, Instagram, YouTube, all those great social media places. I actually downloaded TikTok 2 nights ago and have been playing around with it. So I'm going to have to check out Fiveable on TikTok. That's new to me. So we'll see what kind of content they have. I'm sure it's fantastic. All right. So check us out on the social media sites that I'm sure you're spending a lot of time on while being stuck at home. All right. So in this stream, first of all, we're just going to review some probability rules and notation, also some definitions and things like that. We'll spend a few minutes going over those because I know that those things can be a little bit cumbersome, and it doesn't hurt to review those every time we talk about probabilities and make sure you know what's going on. We're going to look at how to create a tree diagram. Then we're going to look at how we can take a problem that looks like a tree diagram problem, and instead of drawing a tree diagram, approach it with a two-way table by doing a simulation. Okay. Whenever I learned this method, I thought it was really cool because I prefer a two-way table when calculating probabilities. Tree diagrams can be really tough to interpret where the and probabilities are, where the conditional probabilities are, and all those things. But a two-way table makes more sense to me. So, and you can approach any problem with a two-way table. So we're going to break that down. And then we're going to look at a COVID-style FRQ practice question. Kind of an extended FRQ, maybe a 25-minute question. I think it's 5 parts. We'll see when we get there. To help you to see what maybe to expect on the free response this coming year on May 22nd. All right, so some quick definitions for probability. We're not going to spend too long here. If you see the U, it's like a large U, that means union, which is kind of easy to remember. And kind of the non-math word for that is or. Okay, so the union is the probability of event A or event B. So the probability that one or the other is occurring. Okay, not them both occurring at the same time or both occurring together, but just one of them, at least one of them is occurring. Maybe that's a good way of saying it. So the general formula here is to add the probability of A, the total probability of A, add the total probability of B, and then subtract the overlap. So subtract the probability of A and B. That's how you'll find the union probability. A lot of times you'll see the word or, okay? But if you see the notation, it's the U, and then the math word for that is union. And that extends into other areas of mathematics as well, not just probability and statistics, set theory, all sorts of other fancy math subjects. You'll see that. So then kind of the opposite of that is the upside down U, which stands for intersection. Okay, and that's going to be the probability of event A and B occurring at the same time. Okay, we can multiply the two individual probabilities if and only if A and B are independent. And I don't know if this will come up on this year's exam, but in the past, there seems to always be a multiple choice question. Any practice test I've ever looked at where they ask you to find the intersection probability of two events, A and B. And sometimes it's as simple as multiplying those two probabilities. And other times it doesn't give you in the problem that the two events are independent, and therefore you don't have enough information to calculate that. So it's that dreaded E, not enough information, or whatever, however it's worded on that particular test. And generally we're kind of taught to ignore that option. And in AP stats, that is a valid option. So again, I don't know if it'll come up with just the free response this year, but if it did, that's an important thing to note. We can only multiply A times B if the two events are independent. If they're not, you don't have enough information to find the and probability. Okay. So another one that you'll see, and this one's very common in the free response questions, is that little line, okay, like A line B. That means you're finding the conditional probability. Okay, and that's going to slim down your group to a smaller subset of the population. So if I'm finding the probability of it snowing, given that it's December, I'm only looking at the days in December. I'm not looking at all 365 or 366 days in the year. I'm only looking at days in December. Okay, now clearly that probability is going to be higher than the probability of it being throughout the whole year. Generally, that's going to change your denominator. Okay, your denominator gets smaller. Sometimes the numerator also gets smaller, but numerator changes with pretty much any probability you're doing. But with conditional probabilities, the denominator changes from what a typical probability would be. It's usually noted by the words, given that the day is in December, or of all the days in December, what is the probability of it snowing? And then you know that you're only looking at a smaller subset of the population. You're not looking at all 365 days in that case. Okay, kind of continuing that. So independence. If two events are independent, it means that they do not affect each other. So in other words, if event A takes place, event B is not more likely to occur. Okay, so going back to our snowing example. So snowing, the event snowing and the event being December, those two events are not going to be independent of each other because it is way more likely to snow in February than it is to snow at any day of the year. That's a big difference, right? Okay, if we're just looking at the days, if I put all 365 days of the year in a hat, and of course I mix them up because we always do that, right? And I draw one out, the probability of picking a snow day is probably going to be lower than if I just put the December days, the 31 days in December, into a hat and drew out one of those 31 pieces. There's probably more snow days proportionally in just December than there is in the whole year. So that means that those two events are not independent. The fact that it's December is making it more likely to be a snow day. So therefore, they're not independent. If they're the same probability of being a snow day, given that it's December or given that it's just any day in the year, then they would be independent. And that's clearly an example where they're not. Okay. So disjoint or mutually exclusive. If two events are disjoint or mutually exclusive, same word, different, or same definition, different word, they cannot occur at the same time. So the events being 90 degrees outside and snowing are going to be mutually exclusive because it would never snow and be that hot outside at the same time. Okay. I live in Alabama, so it's already really hot here. Okay. I know in some parts of the country it is snowing right now. But for it to be a snow day in Alabama in April is probably not going to happen, although it has happened before. But those two events of being 90 degrees outside and snowing are mutually exclusive because they're never going to happen at the same time. It's impossible. Okay. There's no overlap in those two events. If you're thinking about a Venn diagram, it would be two circles. There's no overlap between them. There's no days where it was 90 degrees and snowy. Okay. Two individual circles not overlapping. So if two events are represented with a Venn diagram and there's something in that middle spot between the two, then they're not going to be disjoint or not mutually exclusive. Any of these various definitions are very likely to occur on the AP exam. I would be willing to speculate and put money on the fact that probability will be on the 2-question free response you'll have this year. If there's anything I'm sure of, it's that probability and inference will be on there. One of those two, or both of those things in some way. A lot of other things that we talk about may or may not be on there, but those two are definitely on there. And probability is always the thing that seems to separate the ones who pass and the ones who are ones or twos. So I really want to make sure that we, have a good definition if you're following along with all the 5 level streams we've been doing. So kind of a good outlook on probability as we continue. All right, so just kind of a quick example here. A group of school-aged children were asked if they ate the school-provided lunches. The data is broken down by age and whether or not they regularly eat the lunchroom food. Okay, so 5 students aged 4 to 8 that responded to the survey said that they do eat the school lunch food, and 2 said no. All right, and then so on and so forth. So the first question is, what is the probability of actually eating the school food? Okay, so y'all take a minute in the chat. Make sure you take advantage of that down at the bottom of your screen. You have the chat over there. It says say something nice. Please keep it nice. It also has, you can ask a question, and either as we're going along or at the end, I can come back and answer your questions. So y'all take a minute over there in the chat and answer that question. What is the probability of selecting yes? And you can leave it in a fraction form. Okay, 25 out of 43. I'm gonna have to check the fraction there. It sounds about right. 58.58. Yep. Kate, that's good too. Okay, everybody in agreement on that? Good deal. I think either one of those answers are perfect. Okay, you're good, Olivia. Either one of those answers are fine. Decimal is good. Fraction is good. I would not spend my time reducing fractions on this year's exam. Such a time crunch with 25 minutes and 15 minutes. And they've said that you don't have to have a calculator, although it could be helpful. So I would definitely not worry about reducing fractions. If you want to divide them and get the 0.58, that's fine. If you want to leave it as 25 out of 43, that's fine too. Either one of those two options I would go for. Okay, so yeah, 0.581. All right, so then on part B, it says find the probability that they would say yes, given that they're in the 9 to 12 age group. So y'all take a minute and redo the problem for this conditional probability. All right, we got 12 out of 26. A few of those. You may have the decimal form. .46. Yep, sounds like a little bit less than half. Okay, good deal. Yes, that would be it. All right, so just to reinforce here, because I am a huge fan of two-way tables, and that's the way that I like to break things down. So if I'm looking at the problem, given that age 9 to 12, I'm only looking at this column. I can forget about this column and the totals. I just want that 12, 14, and 26. 12 of them are yes. There are 46 or 26 total. So I am 12 out of 26. Okay. When you see given that, or of the age 9 to 12, what is the probability that they would eat school lunches? That could be another way they could say it. You're just going to block out whatever that subset of the population is. Normally on a written test, I would say like circle that column or circle that row. All right. If this were reversed and it said probability 9 to 12, given that they said yes, it would be 12 out of 25, because given that they said yes, would just be looking at the first row. So the conditional probability is either going to block off a row or it's going to block off a column. Okay. In this case, it blocked off a column. All right, so C, using our answers from A and B, are the events yes and 9 to 12 independent? So what do y'all think? Are they independent of each other? What do y'all think? Yes or no? No, because the probability is less than that of the others. Okay, that's one way of saying it. The probability of yes, given that it's 9 to 12, is less than the probability of yes overall. Okay. Really, they just don't have to be equal. Okay, as long as they're not equal. Sorry, my little tab is coming up. I need to keep my cursor over there. So one way of saying it is, since 0.581 is not equal to 0.462, the two events are not independent. The age level appears to have some impact on whether or not a student eats lunch at the lunchroom. And you can see that with the other classes as well. Yes. Okay, Josie, that was a good explanation as well. If you're asked a question like this, which I think is very, very likely, or at least very possible, make sure that you include context. I said age level has some impact on whether or not a student eats lunch at the lunchroom. And then I compared them and said the two probabilities are not equal. Therefore, they're not independent. If the two probabilities are equal, then they are independent and they have no impact on weather. Okay. But anytime you're answering a question, just be sure to include context with your numbers or with your justification in this case. Okay. So we're used to seeing questions like this. Last year's AP exam, number 3, which Trevor Packer said was like the question that separated the two groups. Okay. There's generally always a question, and it seems to always be the probability question. It was very, very similar to this. So you had a part A that was like 3 probabilities, like A and B. You had a part B, which was on independence. And then part C had some other aspect to it. I can't remember off the top of my head. But to me, A and B were easy. C was kind of tough. But you can kind of expect that. Okay. I would not be shocked to see a question similar to this on this year's exam, and then mix in something else. Okay. So D, find the probability of yes with the union, or you could change that to or. So yes or 13 minus 18. So y'all take a minute and do a little bit of math and give me an answer on that one. What do y'all think? What's your final? Probably need a calculator for this one, so it might take a minute. Okay. We got 2 answers. We got 35 out of 43 and then 27 out of 43. And there's one key difference between the 2 answers that we have over in the chat. And that is, it looks like Josie subtracted the overlap. And Kate, that might have been what you forgot to do there. So anytime you have the or, so you take 25 total people said yes, and 10 total people were in the age 13 to 18. However, we're counting these 8 students twice, because we counted them as part of our 25 and we counted them as part of our 10. So we want to take away one of those times that we counted the 8. So we do want to subtract the 8 out of 43, which gives us the 27 out of 43. So it's really important to remember to do that. Also, I would note that showing work is very important on these as well. There was an AP exam question 2 or 3 years ago that was similar to this, and half of the credit was showing the work, half the credit was getting an answer. So if you would have had, what Josie has in the chat would be great. That's work and the correct answer. But if you had just an incorrect answer with no work, then you would not get any credit. But you could have some work leading to an incorrect answer and still get credit. And I think, I just want to make sure you guys maximize your credit as much as you can. So yeah, 25 plus 10, and then we got to subtract the 8. Find the probability of yes and, so sometimes they'll say the word and instead of putting the intersection symbol, ages 4 to 8. So how many students are in the yes and 4 to 8? So this one should be pretty quick. Five out of 43. Yes. Okay. So on this one, both of these, there's nothing to change the denominator. There's no condition that slims down our population any. We're looking at the whole group of students in our sample. Okay, so we're looking at all 43. That's why our denominator on both of them were 43. Are the events yes and age 13 to 18 mutually exclusive? No, because there were 8 students who were both yes and age 13 to 18. So if that were a 0 there, they would be mutually exclusive. I've never seen a question where they use that definition on a free response, but I could see this year. It's a very easy question if you know the definition. But maybe instead of independence, doing mutually exclusive, since they want to make sure that you can apply things more as opposed to kind of spitting out the same answers that you've seen over and over. So I did kind of throw that in there as well. Okay. Any questions on that example there before we move on and look at tree diagrams and how we could compute things a little bit differently? All right. So tree diagrams. So tree diagrams are a great way to organize data when you're given 2 events and the probabilities are given as percentages. So if you have a word problem where you have, this percentage of people said yes, and this percentage of people changed their mind after reading something. Okay. So you have yes percentage and then change their mind percentage. Then a tree diagram is a great way to do that. However, sometimes whenever you have more complicated probabilities like and, or probabilities and conditional probabilities, to me, it's hard to read that from a tree diagram. It's not wrong to do it with a tree diagram, and that's probably the more conventional way of doing these problems. But I want to give you another option if you're more comfortable with 2-way tables like I am. So that's what we're going to be focused on. Also, without having conditional probabilities, and then or and probabilities, exclusivity, mutually exclusive, and independence can be difficult to prove. Because if you don't have a conditional probability to compare it to something, or maybe the probability of the event A, but maybe, event A was the second part of the tree diagram, then you have to add up to, and that can be also kind of tricky. So you can approach it with a tree diagram. So here's our example. Mount Laurel Pharmaceutical Company has developed a new, more cost-effective way of determining if someone has developed antibodies against the varicella virus, which is chickenpox. However, they have found that there are some minor problems with their tests. 75% of the tests come back positive. However, of those tests, that sounds like a conditional probability to me, 10% show a false positive. Also, 12% of the negatives are also false negatives. That's also a conditional probability. 12% of the negatives are false negatives. Okay, so here's kind of what your tree diagram would look like. I had to go to a new slide there. Same thing here. All right, so we're doing our antibody test. So we have 2 options, right? Positive and negative. What percentage of the tests are going to come back positive? 75%. Oh, well, we have the rest of our, we have positive that's true positive, positive that was a false positive, negative that's true negative, and then negative that's false negative. Okay, so 75% is going to be positive. Then what percent is going to be negative? 25, exactly, right? Because it's the complement. So I'm going to put 0.75 and then 0.25. And it says of the positives, 10% show a false positive. So that means that 90% of those are true positives and 10% false positives. With negatives, 12% of the negatives are false negatives, 88% are true negatives. Okay, so that would be kind of how your tree diagram. I also go ahead and stress to calculate the and probabilities down the side. That's simple. All you're doing is multiplying 0.75 times 0.9 equals 0.675. Okay, and then working your way down through here and then through the negative branches as well. Okay. So that is how you can go about doing that with a tree diagram. All right. Now, if I were to ask you, what is the probability of having a true test? A lot of people would add up 0.9 plus 0.12. 0.9 plus 0.12 comes out to be 1.02. Is 1.02 a proportion? No, it is not, because it is more than 1, right? And if we have a proportion more than 1, that should cue us that something's off. What you would actually do if you were calculating the probability of having a true test, I guess I should have said 0.9 plus 0.88. Either way, still more than 1. You would do 0.675 plus 0.22. But a lot of times this and column is not there, and it gets really tricky. You add up two proportions, and all of a sudden they're not adding up to be 1. Or they're adding up to be more than 1, and you're kind of stuck. Okay. So let's look at this problem from a different approach. We could calculate them using a tree diagram. However, sometimes that can be a bit cumbersome to decide what my population is when the question is a conditional probability. So of the true test, what percentage are positive? And then you would have to find all of the true tests and find the true positives and divide it by that. And it just gets really, really weird. Or maybe it's also hard to see what probabilities are in the diagram, which ones are and, which ones are or. It kind of gets tricky. So I introduce you to simulation. Okay, maybe y'all aren't excited about that as I am, but it's a nice little break in the math to have a nice little cool old school Google Slides animation zooming in at you. I just picture in my mind the Minions. If you watch the movies and they're like illumination, that's what I picture when I was saying that. I think I didn't do a very good job of imitating that. But anyways, okay, so we'll move on. So anyways, simulation is a really cool way of taking an event like what we just looked at with the drug test and approaching it through a two-way table using proportions and percentages that make a lot of sense. Okay, so we're going to simulate that. So we're going to take the same problem we just did, okay, and we're going to simulate it with 1,000 people. 1,000 people is a great number to use because it makes our calculations really easy. Okay, 75% of 1,000 people is 750 people. The answers are right there in the percentages. Okay, all right. So we can set up a two-way table with pick a number, 1,000 people. We also could do 100 people. That's another really easy round number. You could do 10,000 people. Technically, you could do it with 10, but that would make for some weird decimal amounts of people, and that's just kind of strange. But 1,000 people is a good number. That's the one I always kind of go to. It's going to minimize the amount of decimals you have for people, which is kind of weird, but you still have to go with it with the math, and it makes the math easy. So we have 1,000 total people. So we have two options. We have positive or negative, and then we have true or false tests. So we have true positives and false positives. We have true negatives and false negatives. And then we, of course, have our totals. All right. So the first one we had was it said that 75% of people test positive. That's 750 people. All right. So if 750 people test positive and there's 1,000 total people, what number of people are going to test negative? 250. Exactly, Katie. Okay. You'll kind of see where we're going here. And if we go back to the problem, it says that 10% of the positives were false. Okay, so this number right here, 10% of the positives are false. How many false positives should there be if 750 tests are positive? $75. Exactly. Do y'all see this? To me, this just looks so much better. I don't know. Whenever someone showed me this trick, I was like, yes, this is great. I love this because I hate tree diagrams. I always get confused. All right. So then how many true positives do we have? You got it, Katie. 675. That is it. Okay. Yes. And then, of course, we would calculate the negative values the exact same. 12% of the negatives are false. 12% of 250 is 30. So therefore, 220 are true negatives. And then we can finish it out with the totals because that's easy, right? We can add. We don't do much math and stats, but we still do some math. Okay. And now we've taken that problem that looked like a tree diagram, and by simply saying that we're going to simulate it with 1,000 people, we have a two-way table. Calculating independence now, or testing independence, is way easier. Calculating an OR probability is way, way easier. Okay. And probabilities. You might have had those from the tree diagram, but it still was even easier now. The probability of being false and positive is 75 out of 1,000, which is 0.075. Okay. Really, I just love this. I think it makes things a lot simpler. So now we're set to calculate our probabilities just like we did in the example before, just like we saw in the 2019 test. And it makes things a whole lot easier. So the kind of questions you might be asked: find the probability of the following events. What is the probability of having a false test? Feel free to answer in the chat. Probability of a false test. .105 out of 1,000. Does anybody have anything different? Olivia agrees. All right, we got a percentage answer. Same thing. Yes. Okay. There are 105 total false, and there's 1,000 total overall. 105 out of 1,000. There you go. To me, that's easier than adding up an OR probability from the tree diagram, because you would have had to have taken the positive, or adding up two and probabilities. You would have taken the positive and false from the very end of our tree diagram with the negative and false. But in a tree diagram, it's just right there. But since the true and false was the second event in our tree diagram, it's really hard to see. But a two-way table, there really is no first or second. It's just the two axes. All right, so in part two, the probability of testing false given that you were a negative test. So having a false test given that you were negative. What would our fraction be? 30 out of 250. Yes, which is 12% roughly. Okay, 0.12. All right, so the next one is false and negative. What's the probability of testing false or testing negative and the test being false? 30 out of 1,000, right? And we don't change our denominator. We changed our denominator for the conditional, for the given that, but we didn't change it for the other. Okay, so 30 out of 1,000, which is 3%. All right, based on your answers from A, are the events false and negative independent? Nope, not independent. They're very close though, right? 10.5% is pretty close to 12%, but not quite. So these are the two we're comparing here. Okay. So the probability of being false and the probability of false given that you tested negative. You also could have done the probability of being negative, 250 divided by 1,000, and the probability of negative given that you're false, which would be 30 out of 105. But since it says based on your answers from A, they're going to want you to use these two. So they're going to want false to be event A and negative to be event B. I think one year they counted off if you reversed them, which is kind of strange to me, but you know, I don't write the rubrics. So yes, you're right. They are not independent because the 0.105 is not equal to the 0.12. Testing negative for the virus does affect the probability of getting a false test result. Okay, either false positive or false negative. Negative looks like they're a little bit more likely to be negative than false overall. Okay, any questions on that? Okay, I just love that breakdown of the tree diagram. It was a new concept for me because the tree diagrams can be tough. And I like two-way tables because if I see conditional, I know I can just hone in on the second thing. The negative, I can just hone in on that row and just look at that row. But on tree diagrams, it's not that obvious. So why not just simulate that tree diagram with 1,000 people and create your own two-way table? Okay, so I definitely wanted to share that with y'all this week. Okay, so here is something that you would see this year on the free response. No, they will never. I don't think they will ever require you to do a tree diagram. I think that they would accept you doing a two-way table and saying I would notate simulate with 1,000 people and then draw your two-way table. Okay, you have two options, and the one I just did, it was positive and negative. You can put that on the vertical axis, and then true and false for being the test being right or wrong. Those were your two options, your two events. Okay, and I think one year they said something like the amount of said create a tree diagram, but I think in the rubric it said they would accept if you did a two-way table with a simulation. That was like a little note that they would accept that. The person who showed me this trick is an AP grader and has been an AP grader for a long time. And that was her suggestion for these types of problems. So I think that we would be good to do that. It's a good question, though. Very good question. All right. So something along those lines of what you might have this year. For a study on the effects of a particular supplement on stress, scientists randomly assigned a group of high school students to one of two groups. One group is taking this new supplement while the other is taking a placebo. The study from their results is given below. 70% of the students received the drug, while 45% of those reported a decrease in stress. Of the ones taking the placebo, 22% of them reported a decrease in stress. All right, so we have our two events. Supplement, placebo, decreased stress, not decreased stress. Okay, and you can kind of see that. Traditionally, you would see that and think, I need a tree diagram, right? 70, 30, 45, 55, 22, 78. Yeah. And that would be kind of the way that you would approach that. And that would be fine. You could totally still do a tree diagram. I'm not telling you to not do a tree diagram if that's what you're comfortable doing. I just think that the two-way table makes some of the independence and conditional probabilities and the OR probabilities easier to do. But tree diagrams are completely okay as well. All right, so A, what type of study is this? Is this experimental or is it observational? And explain. So throw that in the chat. Observational, experimental. Experimental because there is a cause and effect. Experiment because treatments imposed. Experimental because they are assigning treatments. Good. Y'all are all definitely on the right track. Okay. This is an experimental study because the supplement treatments are randomly assigned. So notice that I stated clearly what treatments were being assigned. I wasn't assigning the stress or decrease in stress. That is not even possible. And it would be unethical if it was. But I'm assigning the supplement versus the placebo. So the supplement treatments were randomly assigned. This allows the scientists to establish a cause and effect relationship between the supplement and the student's stress level. I would be sure. So like Riley with your answer, it is experimental because of the randomly assigned treatments. Therefore, I can claim a cause and effect relationship. But there's nothing really in the problem that says that it's cause and effect. It says study of the effects, but the randomly assigned treatments is what you're looking for. It's different than random selection. So if you're doing a hypothesis test and it's an experiment, you need to make sure the treatments are randomly assigned. If you're doing one that's an observational study, you just need to make sure that the people were randomly selected. Okay, a simple random sample. But if it's an experiment, you need randomly assigned. It's a difference there. If you quote the problem for your random check, you should be good. Okay, so yeah, this allows the scientists to establish a cause and effect relationship. Exactly. But those are the two things in bold are the big things we're looking for. If I were a betting man, which I'm not, I would put money on the fact that you will see this concept on the AP exam. It is like to me, it's like the golden rule of statistics, one of the golden rules. It's one of those things if you learn anything from AP stats, this difference here is really important because you see studies all the time online that say that blank causes blank. Okay. And technically you really can't say that it causes that. Smoking causes some disease, whatever, insert. You can't necessarily say that it causes that. You can say that they're correlated, and of course they probably are strongly correlated. But for something to cause it, you would have to assign the smoking treatments, and we all know that's unethical. Okay, so if you assign treatment A, treatment B, and compare those, then you can say that something causes something if you get statistically significant results. But if you just observe people, you can't establish cause and effect. It's just a huge idea, and it's way misused in the general world. In terms of articles people share on social media and things like that. So this concept, probably every week that I'm doing streams, it's going to show up. Okay, just because I don't want you guys to miss that. All right. So part B, in conducting the experiment, a scientist has randomly selected 1,000 students to participate. Explain how the scientist is going to randomly assign the treatments. So he randomly selected 1,000 people. Okay, but now he's going to randomly assign them. All right. This should look familiar to a lot of you. First, the scientist is going to label each student with a number 1 to 1,000. This is one way of doing it. Next, the scientist is going to place the 1,000 numbers in a hat. Before he starts drawing names out of the hat, what should he do with the numbers? Make a key. Yeah. Okay. Not the one I was looking for, but you're right. If you label each student with the numbers 1 to 1,000, I think that covers making a key. You know what number goes with each student. To me, that was the idea of making a key. And then you put them on a hat. And before you start drawing them out, what do you got to do to those numbers in the hat or names in the hat? Shake them up. That's right. Mix them up. I hinted at that earlier because I was like, oh, it's coming up again. I want them to remember that. Okay. You got to mix them up. You also could have flipped a fair coin. There are ways of detailing that to make sure that you use a fair coin to determine who goes to which group. Maybe the first, it said that 70% went to the drug. So it's not going to be 0 to 499. So you also could have numbered them 0 to 999. But this one is not an equal sample. Okay, I kind of threw a little bit of a curveball there to you as well. So maybe you could have flipped a coin, and the first you know, you could have said the first 300 that get heads get the placebo, and then the other 700 get the other treatment. Doesn't seem as random to me as putting them in a hat and mix them up. The hat mix them up is always the method I've went with. You also could have used a random number table. In that case, you would have to start with 0. And I'm going to put it in the chat. So you would number them this way. Okay. If you were doing a random number table, it would have to be 000 to 999. And then you would go through and, you know, the first number, you would pull them out and keep going. Okay. This one is a little bit different because it's not 500 and 500, because it says that 70% went to the new supplement, 30% went to the placebo. All right. So it's not 50-50. And you don't have to have equal treatments. Both are large enough. All right. So yeah, mix them up was the main thing I was looking for. A lot of ways you can randomize things. These rubrics on the AP exam site, you have a ton of different options. Okay. There is a way to do it with a fair coin. I'm just not as familiar with it, especially in this one where the samples, the two treatments are different sized. I think the easiest way of doing it is either this way or a random number generator to select the first. So next, the scientist draws 700 numbers. The 700 names tied to the numbers drawn will receive the new supplement. The remaining 300 names will receive the placebo. Okay. So you could have done a random number generator, and the first, do you have to mention no replacement? Yes, that is a good note. Okay. So I would add that in, draw 700 numbers without replacement. For sure. I should have added that to my slides. I need to add that before, after I finish this. So I'm going to make a note to do that actually. Good catch. Good catch there, Kate. But yeah, I don't know what way your teacher has went about going over that randomly assignment process. This is the way that I generally go. It's just, I think, to me, the easiest way of getting the most credit without having to remember a lot of things. Mix them up, and then the without replacement. If you have those two things, you should be good. Okay. So yeah, make sure you know how to randomly assign treatments. Okay. All right. So C, with 1,000 subjects, the scientist wants to know the following probabilities. Probability of receiving a placebo. That one should be easy. Probability of receiving placebo, given that they had a decrease in stress. To me, that one's a little bit tricky. And 3, a decrease in stress. We're going to go about it with our two-way table, okay, which I kind of led into that because we assigned 1,000 subjects with the last one, okay. 700 and 300, okay. The percentages were, I need to go back. Well, let me go back now. Using the percentages you would have, this is what it would break down to be: 700 and 300, based off of the 70% that received the new supplement, 30% received the placebo. I don't know why it's not letting me go back. Here we go. %45% reported a decrease in stress, and then 22%. Okay, so 45% of the 700 is 315. This is the 55%. 22% of the 30 is 66. 234 is the complement there. They add it to be 300, and then you can add those up. Now these three probabilities are super easy. All right, placebo, we had 300 out of 1,000. Okay, 30%. That one you could have done without the two-way table. This one right here is going to be a little bit more tricky. 66 out of 381. Given that there's a decrease in stress, that means I'm only looking at this column. So 66 out of 381, 17.3%. the probability they experienced a decrease in stress, which is 381 out of 1,000, 0.381. Okay, that one is really easy with a two-way table. With a tree diagram, you're going to have to add up 2, since that would have been the second event in the tree diagram. You would have had to have added up 2 of your and probabilities on the very end of the branches. And that's one where I'm just like, I don't really know how to do that. And it's really hard to try to teach people that as well. But the two-way table, it's just really obvious. You got to do a little bit of work in the front end to get the simulation of 1,000 people. But once you do that, it just kind of works itself out. Okay. D, to test his 2 proportions, the scientist decides to perform a 2-prop z-test for the difference in true population proportions between the supplement and placebo group. Okay. So we have 2 proportions. We have the proportion that decreased in the supplement group and the proportion that decreased in the placebo group. To ensure that we can perform the test, one thing we have to make sure of is that both groups have at least 10 successes and failures. Explain if this condition is met and why it is necessary that it is met. So what condition is this describing here? We have 3 of them we always check. Which one is this? Which of our 3 conditions of inference are we checking with this particular breakdown? The 10 successes and failures. Normality. Yes, you're checking normal. Okay. In the past, this was always incorporated into a question where you did the SPDC or the phantom outline. It's probably the way your teachers have taught that. And you just said normal, and then you did the little formula and proved it. Okay. With this test, since it's not incorporated, they might want you to be a little bit more specific. All right. Using our two-way table, we can see that 315, 385, 66, and 234 are all at least 10. This is important because it ensures that the sampling distribution for the difference in 2 proportions is approximately normal. This will allow us to calculate the probability of achieving these 2 samples, given that the population proportion of both groups are equal. So it's allowing us to do that p-value. So the p-value assumes that the 2 proportions are equal and generates a sampling distribution of sample size 1,000. And then of all the possible samples of 1,000, the probability of getting the sample that we actually have is what our p-value is, or that number or less, because we're doing a tail probability there. But it assumes that they're equal and calculates the probability of getting that number or less, or that number or more. And if it's two-tailed, multiply by 2. Okay. But that being a little bit more specific, that it's the sampling distribution, and in this case, for the difference in 2 proportions is approximately normal. That's what you're trying to check, so that you can use your normal, your normal calculations for a z-score to get your p-value, or a t-score if it's means. Okay. All right, last one. In running the test, the scientist achieves a z-score of 6.8632. Use this z-score to justify at the 0.05 significance level if the 2 proportions are significantly different. Again, I threw a little bit of a curveball here. What do we normally justify with our 0.05? Normally, we don't use z-score. What do we normally use? Our p-value. Okay. Normally, if your p is low, you drop the hoe, right? If your p is not low, you fail to reject the hoe. That's normally our litmus test, is comparing the p-value. However, you also can make conclusions from your test statistic. That's why they've always required you to write that down in the question. Okay. They've always required you to put that in the work. And somewhere in your Phantom or in your SPDC, you have to put the test statistic, either your t-score or your z-score, depending on if it's means or proportions. Okay. Is a z-score of 6.8632 a standard z-score? Is it, I don't want to say normal because that's not what I'm going for. I'm not talking about the normal curve. Is it ordinary? Is it ordinary to have a z-score of 6.8632? Yes or no? No, it is not. Our z-scores are normally between, almost always between -3 and 3. Because remember, a z-score is how many standard deviations are you above or below the mean. And if you're talking about a normal curve, think back to the empirical rule, 99.7% of all your data is between 3 standard deviations. So your z-score is between -3 and 3. If you're doing a 0.05 significance level test, then that means that you should be within 2 z-scores, 2 and -2. All right. But a z-score that's this outrageous, all right, our z-score is more than 3, is a very highly unlikely result to achieve. Therefore, our p-value would be very, very low, likely close to 0. Since our p is more than likely less than 0.05, we reject our hoe that the two population proportions are equal. We do have convincing evidence at the 0.05 level that the true population proportion taking the supplement who experience a decrease in stress is higher than the proportion of people taking the placebo who experience a decrease in stress. All right, so it's kind of along the same lines of that p is low, drop the hoe, but we don't have the p-value, and they didn't give us, I mean, I guess technically you could have typed it in your calculator and gotten the p-value, and maybe that's why they say the calculator could be useful, but not necessary. They give you the test statistic and want you to justify your result from there, but technically you could just calculate the p-value. It comes out to be 0, okay? But yeah, a z-score outside of 2 and -2 is probably going to be a statistically significant value enough that you can reject the hoe. All right, which the hoe is always that they're equal in this case. And it's actually more than 3, which is way outside the range. If it's a normal curve, pretty much 100% of the data is within 3 standard deviations, which on the standard normal curve is 3 z-scores. Okay. Notice I was just a little bit more exact in the way I'm explaining that than maybe what we have been in the past. Got context, compared the proposed p-value, which we claim is going to be really, really low. It's going to be less than 0.05. Therefore, we reject our hoe. All right. We do have evidence that they're different, or that this one's more, okay, that it's higher. I guess maybe I should have said different since it asked if they're significantly different. We know it's higher, though. We can tell from looking at the numbers. Okay. All right. Any comments or questions? It's been right at an hour. I know you guys probably are ready to hop off of here. Any questions before I close this down? I'll stay on a minute or two. I'll be glad to re-explain something that might be a new topic for you, or a familiar topic, but a new way of approaching it. So I want to make sure that's clear to you if that's a strategy you want to use on the AP exam. I don't want to undo anything your teacher's already done, but I want to give you another out if you need it. All right. Don't see any questions. Thank you guys for joining. I hope you will check out all the other streams on Fiveable, and we'll be back here next week, same time, same place, looking at, what was it? Combining random variables, okay, which is definitely something that I would need to review if I were taking the AP test in May. All right. Y'all have a good week. Hope you're all well. See you next time.